Ladies and gentlemen, welcome back to Engineering Dynamics. In this video, we will talking about the eigenfrequencies and eigenvectors of a continuous system. So in the last videos, we always had a mass, stiffness, and damping matrix, or a gyroscopic matrix in some cases, and we had a discrete system, so we had points of masses. Now we're talking about a continuous system where we technically have infinitely many masses, so we're also having infinitely many eigenfrequencies and eigenvectors. So let's look at our system. What we are trying to solve or to understand are the eigenfrequencies of a system that is a simple bar that is fixed on one end and also fixed on the other end. When we derived these equations, we talked about a system that is only fixed on one end, but now we're looking at a system that is fixed on both sides. So to recap, we had our differential equation in space and in time of our beam, and we had boundary conditions. So possible boundary conditions are that we prescribe a force or a displacement. Now we have, because we have a fixed bar, we have zero displacement here, and we have zero displacements at the end. So at the beginning and of the end. And with these two equations, we will get an analytical solution for the eigenfrequency and the eigenmodes. If we use the Rayleigh Ritz approximation, we do that by approximating our displacement field in space and time, where we say, well, we provide our shape function, so the function that the system could take, and have them overlap in such a way that they fit the system as good as possible. We'll never be able to get the accurate the solution of our system if we're not choosing the correct eigen shapes of our system. So if we know the analytical solution, we can use the Reilly Ritz and get the same thing. But if we don't know the analytical solution, we can propose we can propose functions that our system could look like for example, like this or like this. And we say, well, if we propose these functions, how can we fit them as good as possible? So we have our shapes and we have our time frequencies or our time functions, which is governing basically the amplitude. For example, we have a cosine or a sine. So the boundary conditions that our function have to fulfill is, first of all, that they are continuous, so we can derive them. So we can't use like step function or something else. And they have to satisfy the boundary condition. The boundary condition in our case is that it is fixed at x is equal to 0 and at x is equal to L. So we have length L. We have the area, the density, and the Young's module. To get the eigenfrequency, to get the frequencies of our discretized system, which we discretized with our function, we of course need the mass matrix and the stiffness matrix, where the mass matrix is F transposed F integrated over X. So we have it will look like we have our function F1, we have our function 2, we have our function 3, and then this is our vector times our F1 F1, F2, and F3. So we will get a matrix and we integrate it from 0 to L, so over our whole domain. We do that same for the stiffness function, but in this case, we're not using the F function, so the shape functions, but a derivative. So this is our matrix B, where we derive our shape functions once with X and just do the same matrix or build the same matrix with B transposed times B with the Young's module and our area of our beam. So A is constant. If we have conditions, for example, we have loads at the end or loads per unit length, we also have a G matrix. So we have F transposed times N plus an integral again from 0 to L, F transposed times our force over the length, and again integrated over X. But we will ignore this for now. So if we are, as soon as we have the mass and stiffness matrix, we can put it into our system, and then it's the whole spiel again where we did the eigenfrequencies and eigenvectors. So or the eigenfrequencies, because the eigenvectors or eigenshapes we already know, because this is our f that we propose. So now we are interested in getting the eigenfrequencies. So the eigenfrequency is in our time function where we have a times cosine omega t and b times sine omega. So this is a very general solution. So this is a general solution because if we derive it once and then we derive it twice, we will get the same thing. And this is exactly what we need for our discretized system. So let's propose two functions. So we have function 1 with x squared divided by L squared minus x divided by L plus x cubed divided by L cubed minus x squared divided by L squared. And these two functions fit our boundary conditions, that it is 0 at the end. And we have our the continuity, so we can derive those functions. So if we derive them, we have 2x to the divided by L2 times minus 1 over L and 3x. Sorry, there must be a squared, and there we go. There must be a, like this. Because if we derive it once, we will get a 3 here, minus 1, that is 2. So these are our two derivatives, which will form the B matrix. So if we now follow this form, we will get this mass matrix and this stiffness matrix. Let's look at the mass matrix where we, for example, want to get this 130. This is achieved by doing the integral from 0 to L times our mass per unit length, which will equal to the mass because we integrate over the whole length, times what was our first function? That was, oh, there it is. We have x squared minus divided by L squared minus x minus divided by L. We square that because we have this transposed. So we multiply f1 with f1 and do it over dx, and we will get m times 1 over 30. And we do that for all functions, and we will get a 2x2 mass matrix and 2x2 stiffness matrix. So now we can just propose here, we say, well, we can just use this system, so this time function, because if we derive it once and we derive it twice, we will get our q's and q dots. Or we could have used this one, but a and b will be determined by our initial conditions. So we can just say, well, if we know the initial conditions, we can just use another one. So just the cosine, we derive it once and twice, and we get the omega and a minus, of course, which will bring us to the same form that we had so many times in the last videos. So we have the stiffness matrix minus omega squared m. We're not interested in the trivial solution, so the determinant is equal to 0. And the determinant is equal to 0 when we have omega 1. So the first eigenfrequency is 10 over km, and the second eigenfrequency is the square root of 42 over k over m. And from that point, we know that these two eigenfrequencies are definitely higher than the ones we get with the analytical solution. Because if we use the Rayleigh Ritz approximation, we will never be able to solve the differential equation exactly, because we have those residuals, so it's kind of like reaction forces. And those reaction forces are like constraints. And if we add more constraints to our system will become stiffer. And if it's stiffer, it will vibrate faster, so the frequency will be higher. So we know that our analytical solution is definitely lower than these two eigenfrequencies. If we know that, we can now use the analytical solution to get our exact eigenfrequencies. So this is the analytical solution. Switch back to purple. And we start from our differential equation. So we had our differential equations derived twice in space. So dash dash is a space derivative, and dot dot is our time derivative. And we propose again the same structure where we have a time function, a space function, and a time function. So we can move m and u to the right, and we know that our system, because if we import that here, we will always have a f and a q. So this one becomes this one, and this one becomes that one. So the u is replaced with f and q and derived once, either twice in space or twice in time, and we will get this equation. We can derive it divided by f. So f goes into here and q goes on that side, and we will get this equation. So we know that this is dependent on time and this is dependent on the space coordinates. So we will have a equality in time and in space. And we know that these two will always be a constant. We don't know which constant, but we will know that they are constant. So from that, we can just reformulate our system, and we see that q double dot is q times our normal q, which is, and for the function in the time, the space derivative, so dash dash is the space derivative, it's km divided by Young's module times area times our space function. This is this one right here. So it's just simple reformulation to get to this part. Now we propose a general solution where the time function is a sine times omega t times, or plus, that's wrong, plus cosine omega t, and our space function is c times sine lambda x plus d cosine lambda x. So here we are, this is our time function because we're dependent on time, and the f of x is dependent on our coordinate. If we derive our system, so if we propose this structure and we insert it back here, we will see that we get this equation, and we already know that our k is minus omega squared. If we do that for our derivative in space, we have minus lambda times f, so this is equal to that. And we know that km divided by Young's modulus area is minus lambda. Now we can fuse those two together, and we will see that omega squared is equal to lambda squared E times A divided by mass per unit length. And we know that because these are fixed to a constant. So this is how they are related. Now we want to solve the initial conditions, because if we know that this is our frequency, eigenfrequency, we can insert it back into our time function. But we have to get the accurate solution, we will we need now to insert the boundary conditions. And our boundary conditions are that at every time point at 0, x is equal to 0, we have 0 displacements. So that means that our space function, so f of x at 0 must be 0. So this will lead us to d is equal to 0, because if we insert x is equal to 0, this will be 1, but we don't need it to be 1, we need it to be 0. So d is equal to 0, and this is gone. Then we do the same thing for L, where we input f of L is equal to 0, and we will see that c times lambda x, in this case lambda x is L, must be equal to 0. And the sine function is 0. Let's plot the sine function like this, where we hit p and 2p, and 2 pi. This means that our lambda is p divided by L times n, because we can be 0 at p is equal to 1, p is equal to 2, p is equal to 3. So we have this one as infinitely many solutions, which then again means that our eigenfrequency is, we can insert this one right here, and we will see that we have infinitely many eigenfrequencies, which is also expected, because if we have infinitely many masses, because we're a continuous system, we will get infinitely many eigenfrequencies, and these are the eigenfrequencies. And we can insert those eigenfrequencies again into our space function, so f of x, because this is our lambda. This was wrong. We don't insert the eigenfrequency, we insert the lambdas, and we will see that this is our infinitely many possible eigenshapes of our system, so which the system can take. So we have, for example, we have something like this, we have something like this, we have something like that. So the most important part to understand is that at the beginning and at the end, we're always equal to 0, because these are our boundary conditions. So we have infinitely many eigenfrequencies that are just a factor of pi. This might be a little bit too complicated, so I have another 2 examples that are more similar to the derivation we did in the last video. So now we have just one basis function, and now we have the end is free. So this will influence our boundary conditions. And we propose another function, so it's just x divided by L. And we have our physical solution is our amplitude, or our space function in space, and this is our time function that modulates our amplitude. To get the mass matrix, we do the same trick that we did before. That is this one right here, where we have F transposed F, but in this case we have F is equal to, or the length of F is equal to 1. So we just square the function and multiply it out, and we will get ML over 3. For the stiffness matrix, we derive it once, and we get L, 1 over L times squared times the Young's module and the area, and we get EA over L. Now we insert those 2 functions into our solution. So we have omega m double dot mq double dot plus kq, so stiffness and mass matrix. But if we derive our function twice, we will get a minus omega, which means that we have kq minus omega squared times m times q. We can just remove the q, and we will be left with this solution. Normally, we would do now the determinant, but because we are just in the one dimension, so we have basically this is a scalar matrix, we can just simply divide k by omega, and we will get this equation. So we know that the omega squared is 3 times EA divided by ML squared. And now that we know our eigenfrequency, we can propose, or we can solve for the actual time function. So now we get the boundary condition. The first boundary condition is that at times 0, at the end, we are not moving. So this is what our system looks like. We are not moving, or basically we're at position 0, but we can have a speed up or a speed down. So if we say that at length is equal to x is equal to L, we must be 0. That means that A is equal to 0, because if we insert time is equal to 0 here, we get a 1, but it needs to be 0, so A is gone. So A is 0. And now we propose that our system is moving at time is equal to 0, so we have a speed. Let's say we have a speed up, so this will look like this. So we derive it once with time, and we will see that, well, if this must be 1, it is essentially something like this. The cosine turns to 1 because we're at time 0. This is right here. And we know that our B is a factor of 1 divided by the eigenfrequency. And now we know the whole solution for our system. Let's say we have a different system. So let's make a cut here. Let's suppose we propose now a different eigen shape. But this time we, by chance, choose exactly the one that we know is we choose by chance the correct one. So one of the analytical solutions ones. So we propose a system or a function where sine is pi divided by 2L times x. And this is the exact solution that we got out from the from the analytical solution of the free beam when we did the derivation. So we do the mass matrix again and the stiffness matrix by, here we do simple squared function, don't forget the square, and here we do the same thing squared, but, oh, sorry for that. We do the same thing squared, but with a derivative. So that's why we have 2 pi over 2L right there. And we will get mass, this is just the mass, times 1.5, and Young's modulus times area times 1.233. And now we do the same thing we did right here because we're kind of cheating. Normally we should set the determinant to 0, but we are in a scalar space, so we can do that, and we will get omega squared is equal to 2.467. And this is the exact eigenfrequency of our beam when we use this proposed function. So this function and this eigenfrequency are exactly the ones that we would get if we used the analytical solution. Don't confuse that with the analytical solution of, where did we do that? Right there. Don't confuse that with the analytical solution with this part. You see that here we have pi divided by L, but here we chose pi divided by 2L, because once we have this system and this system require two different function, because once just the beginning is fixed, in the example we did before, we had the end, the beginning and the end fixed. I hope this video gave you a better understanding on how to work with the analytical solution of discrete systems if you want to get the eigenfrequencies and eigenmodes, and how to work with a system that you discretized with the help of the Rayleigh Ritz method, and to get the time functions when you have the different boundary conditions. If you have any questions, feel free to ask them in the comments down below. Thank you very much for your attention, and I'll see you next time.